Now we're going to look at common probability language. We're going to start with a set of definitions. I'm going to give you those definitions and talk through them so that you have the opportunity to write down what makes sense to you. And then we're going to work through some experiments in this packet. To do these experiments, you're going to need some things. So I want you to make sure you have those on hand before we move forward. The first thing you're going to need is either a deck of cards, which I strongly recommend. If you have a deck of cards, go get your deck of cards. If you don't have a deck of cards, it's okay. As long as you know what a deck of cards is like. You could pull up a deck of cards on your computer and or another device so that you can look at it if you're not familiar with a standard deck of cards. If you have one though, I seriously recommend you get it because it's going to be a lot easier to make sure you don't make mistakes here. The other thing you're going to need to complete this packet is a pair of dice. Just a pair of standard dice. So if you happen to have a Yahtzee game or any other dice game in your house, go scavenge a pair of dice out of that. If you do not have access to dice in your house, that's okay. You should be able to find a generator online where you can roll a pair of dice. To do this probability unit, you're going to need sometimes just to have one die to roll and sometimes roll two dice. I haven't looked up, but you can do just about anything online. So I'm certain that you can generate random rolls of dice if you Google that. So that when we get to the part where you are performing the experiments, you can actually perform the experiments either by hand, which is more fun, or by pushing a button on your computer. Okay, so let's talk about these definitions. Okay, so here are our definitions for the top half of this page. We're going to talk through them. You can pause and write them down. You take a picture, however you want to do it that you learn the best. I usually learn best by writing, so I recommend that you do that. Probability definitions. First, we're going to define a set. Some of these definitions you will already have from 1350, where you did a lot of set theory stuff. A set is just a collection of objects or elements. It's whatever we're talking about. If we are rolling dice, it's the numbers on the dice. If we're playing cards, it's the deck of cards. If you are surveying people, it's the people in your population. If you're getting socks out of a drawer, your set is the colors of the socks in your drawer. Just whatever your objects are that you're working with is your set. A subset is delineated with the notation A subset B if all of the elements in A are also elements in set B. Now for an example of this, A is my set of odd numbers, 1, 3, 5, 7, etc. B is my set of natural numbers. Natural numbers are my counting numbers, starting with 1, 1, 2, 3, 4, 5. As little kids learn one-to-one correspondence, they learn their counting numbers, their natural numbers. So set A, my odd numbers, are a subset of my natural numbers. An experiment is any process with an uncertain outcome. I'm performing an experiment if I'm tossing a coin, rolling a die, drawing a card. Anything that has an uncertain outcome is an experiment. The sample space, S, is the set of all possible outcomes. So if I'm rolling a single die, my sample space is 1, 2, 3, 4, 5, 6 if it's a standard die, because those are the numbers on the die. The event, E, is what I'm interested in. It always should be a subset of the sample space. For example, if I'm interested in rolling an odd number, then E is the set of values 1, 3, 5, because those are the odd numbers on my die. When I start to talk about probability, I change my notation a little bit. This reads as the probability of E, or the probability of the event. If S, my sample space, has equally likely outcomes, like rolling a fair die, or tossing a fair coin, or drawing a card out of a standard deck, so if S has equally likely outcomes, and E is a subset of that sample space, S, then the probability of E, the probability of my event happening is equal to the number of elements in E divided by the number of elements in the sample space. Let me grab a piece of paper so that we can look at that. So let's say we defined E already as rolling an odd number. So the probability of that happening is going to be 3 out of 6, or 1/2. Because we said that we have my sample space for rolling a die is 1, 2, 3, 4, 5, 6. There are 6 possible outcomes. Out of those 6 possible outcomes, how many of them fit my event, rolling an odd number? Well, out of those 6 numbers, 1, 3, and 5 are odd. So 3 out of 6 outcomes fit that event. The probability of that event happening is 3 out of 6, or 1/2 if I want you to simplify. What if my event E is defined as rolling a 1? Well, in that case, the probability of E would be 1 out of 6 because only one number on the die is a 1. What if I defined my event E as rolling a 7? Well, 7 is not one of the numbers on my die. So the probability of that event happening is 0 out of 6, or just 0. What if I define my event as rolling a number that is less than 10? Well, all 6 of the numbers in my sample space, all 6 of the numbers on my die are less than 10. So the probability of that event would be 6 out of 6 because all of them fit that event, or 1. Based on this, can I get a probability larger than 1? Well, no, because if it's a sure thing, if everything fits that event, then it's everything out of the number in the sample space. That's just 1. That's as big as my probability can get. This event up here, rolling a 7, can't happen, and its probability is 0. So that's going to be the least value for a probability. And this is going to be the greatest value of a probability. Every other probability is going to fall in between. Okay, let's go back to our definitions. E prime, or E apostrophe, is the complement. So E and E prime are complementary events if E is the E and the intersection of E prime is not the empty set. Oh, no. Excuse me. Go back to that one again. E intersect E prime is the empty set. That means they do not overlap at all. And E union E and, this is or, this is and E prime is equal to the sample space. They're complementary events if they don't overlap, they don't share any values, and they include everything in the sample space. So let's look at an example of that. Let's go back to my original event that I talked about. If my event is rolling an odd number, well, that includes 1, 3, 5. What would be the complement of rolling an odd number if I'm rolling one die? Well, the complement of that would be rolling an even number. My even numbers on the die are 2, 4, and 6. If I look at E and the complement, and I think about where they intersect, what they share, they don't share anything. If I look at E or the complement, if I include every value in E or E prime, I have 1, 2, 3, 4, 5, 6. That's the entire sample space. That's everything. Nothing's left out. This means that these two events, rolling an odd, rolling an even, are truly complementary events. Okay, the probability of the event plus the probability of its complement is always going to include everything, so that's 1. Which means that if I turn this around and I know, let's say I know the probability of the event, but what I need is the probability of the complement, I could just do 1 minus the probability of the event, and that gives me the probability of the complement. So therefore, there's a conclusion we can make from that. Those three little dots in a triangle just means therefore. So if the probability of the event plus the probability of its complement is 1, which is the case if they're truly complementary, therefore, I can start with 1 minus either of the probabilities and I get the other. So the event, the complement of the event is the sample space minus what's in the original event. That's a separate statement from what I just concluded. Okay, now we are going to go ahead and talk about theoretical and empirical probability, and then we will look at the next page. I know it says before we define these last two terms, let's explore, but we're going to go ahead and define theoretical and empirical probability. To help you remember which one's which, empirical starts with E and experiment starts with E. Our empirical probability is the same thing as our experimental probability. The theoretical probability is based on the sample space, but the empirical or experimental probability is based on the outcomes of an experiment. So if I'm dealing with theoretical probability, I'm looking at the sample space. The probability of an event happening is the number of outcomes in the event divided by the number of outcomes in the sample space. Like my probability of rolling a 1 on a fair die is 1 out of 6. But the theoretical probability is not always the same as the empirical probability. If I actually roll the die 6 times, I'm not guaranteed that one of them will land on 1. I'm just not. It doesn't happen that way. Empirical or experimental probability is based on the experiment and the number of times you do it. To find the empirical probability, I take the number of times my event occurs divided by the number of times I did the experiment. So let's say we know that my theoretical probability of rolling a 1, my theoretical probability of rolling a 1, my event is roll a 1, okay? Fair die, rolling a 1. That's my event. The theoretical probability of that is 1 out of 6 because there's 1 on my die that has 6 sides. There are 6 different outcomes in the sample space. That's theoretical. Experimental, though, or empirical probability is based on how many times I actually do the experiment. Let's say I roll my die 12 times and I get 5 1s. Well, my empirical probability comes out to be 5 out of 12 because I rolled 12 times and 5 of those rolls landed on a 1. That's almost a half, right? 6 out of 12 would be a half. That is not the same thing as my theoretical probability. Did I roll it wrong? Well, no. You might roll your die 12 times and not ever land on a 1. You didn't roll it wrong either. It's just that when we perform an experiment, if I only do a few repetitions, I could get a streak. Like I could roll that die 12 times and I could land on a 1 every single time. It just happens sometimes. Or I could roll it and not ever get a 1. Or it could come out so that it's almost half the time I get a 1. If I'm doing a small number of experiments, we're not guaranteed to get anything close to our theoretical probability. Later on, we're going to talk about what we call the law of large numbers that tells us that the more times we perform an experiment, the more likely we will get a result